Okay, welcome folks, and in today's video we're going to talk about Hess's law. Hess's law, there's a lot of S's in there. Might be a couple of S's too many, but there is definitely a lot of them, and that's why I've got the snake in there, and we'll come back to that snake as we describe what it is. So it's important to note that even though we may have learned how to do calorimetry and what that is earlier, that certain reactions cannot be measured by calorimetry. Very dangerous reactions, some that can't be performed, very slow reactions, and in some cases it's just not practical to measure by calorimetry. So another method is required. And Hess's law is a law which states that, or is built on the fact that net changes in properties of a system are independent of how the system changes. So in other words, what's important is what you begin with and what you end up with, and not what happens in between. So we're just going to use the metaphor of a snake, and maybe there's a couple of ants trying to get from A to B, and they're going to use the snake's body as a slide, and they're going to go on a nice little circuitous route to get from A to B. Now they could also use the direct method shown in the diagram by the orange arrow, and ultimately where they began and where they end up with is the same no matter what route is taken. And that's something in chemistry that's called state function, and it's very, very important and allows us to use Hess's law. So what does that have to do with enthalpy changes? Well, even if a set of reactions occur in a different way or set of steps, the reality is that if the final products and reactants were the same, then the overall enthalpy change is the same. So what does that look like? Well, Hess's law states the enthalpy change of a multi-step reaction is the sum of enthalpy changes of the different steps. So if we look at our example in the diagram, we're just going to look at a potential energy diagram. If you don't know what these potential energy diagrams look like, or trying to make sense of them, you can look at maybe one of my previous videos for that on enthalpy changes. But if we look at the diagram, we have situation 1. We have nitrogen and oxygen forming nitrous oxide. And that gives us a enthalpy change of plus 90 kilojoules. And that means that it's an endothermic reaction. Okay, and that heat was taken in from the surroundings to create NO. And then in stage 2, it actually goes from NO to NO2. And in this stage, heat is actually given out to the surroundings. That's called an exothermic change. And so that's a negative 56 kilojoules. Well, if we want to find what this total reaction enthalpy change is, we just need to add 1 and 2. And we get positive 34 kilojoules. So just adding those two numbers will give it to us. So in effect, the enthalpy change 1 plus enthalpy change 2 will give us the overall enthalpy change. So looking at that in steps, if we look at a one-step reaction, this is the formation of carbon dioxide. We can see that a couple of things here. We can see that there's an enthalpy, and that's a negative. It means that it's a exothermic, and this is the enthalpy change for 1 mole of carbon dioxide. And also, we can break that up into 2 steps. We can break it up into the formation of carbon monoxide here, and then the formation of carbon dioxide. And if we do that, and if we know the enthalpy change for each step, we can get the overall enthalpy change for the formation of carbon dioxide. So the enthalpy change of 1 step should be the same as the sum of the changes in 2 steps. Now we do need to make sure that we end up with this reaction here in the end. So let's have a look at what that might look at. So how to use Hess's law? Well, we need to balance. Always balance in chemical reactions. We got to make sure it's balanced. We need to always keep the target in mind. Okay, we need to flip and reverse that sign if needed in order to get that target, in order to cancel. We also need to multiply coefficients sometimes if we need to end up with, for example, 5 carbons or 6 carbons. We would need to multiply that to make sure that we have the correct number of coefficients. We need to write the arrows, the equations, so the arrows actually line up. So that we can add or subtract at the end, and we need to cancel substances that appear on both sides. And then at the end we add the enthalpy changes. And all equations need to add together to arrive at that target. So keep that target in mind. So we're going to look at an example. Determine the heat of reaction for the reaction. And this is ammonia plus oxygen going to NO plus H2O. And we're just going to look at the steps. So we might be given a set of reactions. In your questions, you might be given these set of reactions here. These 3 reactions. And you can see in red that there's associated enthalpy changes, and some are positive, some are negative, so we're going to try to get to make sense of this. So the 3 reactions must algebraically manipulate to the sum of the desired reaction. That's the reaction on top. So we need to make sure that we keep that reaction on top, and those delta H values are treated accordingly. So what do we do? Well, we might break out and think about these in terms of the different components. So ammonia, O2, NO, and H2O. So for the ammonia set, we've got to reverse that second equation and multiply by 2. Well, why do we do that? Because there's 4 ammonia on the reactant sides, and in our second equation there's 2 ammonia in the product side. So we need to flip that so the ammonia is on the reactant side, and we need to multiply it by 2. So it would look like this. Now when we do that, we've got to also multiply the delta H by 2 and change the signs because we flipped it. The oxygen, well, it's found in more than one place, so we're going to skip it. Also, a lot of these are got from combustion reactions. And in a combustion reaction, normally you have more than enough oxygen, it's in excess. And normally the oxygens take care of themselves when you start cancelling out anyway. So the NO, so in order to get NO, well, we need to multiply the top one by 2 to make sure that we have 4 NO in the product side. So we need to make sure that we multiply the 180.6 by 2. The next thing we need to do is take care of the water. So we need to multiply that third equation by 3. And the reason why we do that is because the third equation gives us 2 water. Well, we need 6 H2O on the product side. And of course we need to multiply the delta H by 3 also. So what is this going to give us? Keeping in mind our goal there at the top of the screen. We're going to cancel terms next and take the sum. So the hydrogens, 6 hydrogens on both sides, might as well cancel those. We got our 2 nitrogens here, sneaky. We got to cancel those, 2 on each side. And we're going to rewrite now that we've cancelled the terms. So 4NH3 plus 5O2, giving us 4NO plus 6H2O. And of course we're going to take care of our delta H, and we're going to get a negative 906.3 kilojoules. Now at this point we probably should check that it's the same as our goal equation, which it is. We've also got a nice tidy delta H, and maybe you want to stop the video and ask yourself, is this reaction endothermic or exothermic? Well, if you said that it was exothermic because of the negative sign in front of the 906.3 kilojoules, you'd be absolutely correct. It is an exothermic reaction, which means that that reaction will give off heat to its surroundings. If you did this in a, were able to do it in a beaker, for example, and you felt the beaker, it would feel warm. So there's a second example on the board. Determine the heat of reaction for the following reaction. We have ethene plus hydrogen going to ethane gas. And we have some following equations that may be used, that you may be given in this practice problem. So again, we're just going to manipulate. We're going to use the first equation as is, because that's what we want in the form that we want. The hydrogen, we're going to use equation number 3 as is, because again, it's on the left, it's as a reactant, and the coefficients are good, so we can use it. And the ethane, we're going to reverse number 2, because we need that ethane on the product side. When we do that, we just need to reverse that sign and make it a positive. Coefficients are good. We're going to do our cancelling here. And once we do that magic didgeridoo-pokery, cancelling these things on either side, our 3 waters, we will end up with the following. So this is the reaction that we want, and we get the delta H that we want. So this is how we use Hess's law. There is an example that I'm going to put on the board now, example number 3. Maybe you want to see whether you can practice that and see whether you can do it correctly. I hope this has helped your understanding of Hess's law. If you like this video, then give us a wee thumbs up, please.